Now that we have seen all the convergence tests, the hard part then is going to be that given a series, how are we then going to decide which test are we going to use? This is going to take a little bit of trial and error, a little bit of experience, and a little bit of problem solving as well. So let's try to see if this guy, the first one here, converge or diverge. If we try the divergence test, so let's try the first one first, divergence test. Then we are going to compute the limit of each of the terms here, cosine of n, when over n squared when n goes to infinity. Now then, we can see that cosine of n over n squared, well, let me do this first. Cosine of n, this is between 1 and minus 1. So if I divide this by n squared, because both of these two guys are going to 0, then I can conclude that this limit is going to 0. Now, because the limit of the terms in this series goes to 0, then that means I cannot use divergence test. It is going to be inconclusive. So let me now try to use the comparison test. For the comparison test to work, I have to compare this series with another one that I already knew whether it converge or diverge. Cosine of n over n squared, maybe I can compare this with 1 over n squared, and we see already that the cosine of anything is going to be between 1 and negative 1, right? So this guy is going to be less than or equal to 1 over n squared for sure. So now, this series should be less than or equal to the series 1 over n squared, where this thing is a p-series with n equal to 2, which is going to converge with p equal to 2. And this guy is going to converge. So it seems like I can use the comparison test and conclude that this guy is going to converge. But there is one problem. And the problem here, the problem in using the comparison test is that the comparison test only works when all terms must be positive. So I cannot use the comparison test, but there is a way to fix this. So let me take a look at the first item here. The way to fix this is that, well, cosine of n, it can be positive. We are not really sure if this guy is positive or negative, but we can actually just take a look at the absolute value. If the series of the absolute value converge, then I can conclude that the original series also have to converge. So this is one of the ways to deal with the series where some of the terms are negative. We can just look at the series where all the terms are positive. So instead of looking at this one, let me just look at this one. Let me look at the series, the absolute value of cosine of n over n squared when n goes from 1 to infinity. So here, this is the absolute value of the original series that we have. If I can conclude that this guy converges, then I will be able to conclude that the original series in the question is also going to converge. Now, this one, all the terms in this series is going to be positive, and I knew for sure that this is going to be less than or equal to the series that we have here, 1 over n squared. Now then, well, because all the guys here are positive, and this is definitely less than or equal to 1 over n squared. This is because the absolute, well, I can do this first. This is going to equal to the sum of absolute value of cosine over n squared, because n squared is always going to be positive. And the absolute value of cosine is always going to be less than or equal to 1. So I knew then that this guy is going to be less than or equal to 1 over n squared, which converge because it is a p-series that we have said earlier. So I can conclude that this guy converges, this guy converges. So that means this guy converges. And because this guy converges, whenever the absolute value converge, that means the original also have to converge. Whenever the absolute value converge, the original will also have to converge. So then I can conclude that the original series here also converge. So that's my conclusion for the first one. Let's take a look at the next one. I have n minus 4 over n factorial. Whenever we see things like n factorial, the first thing that we should try is the ratio test. But let me try the divergence test first then. Divergence test. If we try to take the limit of n minus 4 over n factorial when n goes to infinity, well, this thing is going to be just the limit when n go to infinity of, let me see, 1 over, well, n and n factorial get cancelled out. So I'm going to be left with n minus 1 factorial minus 4 over n factorial. When n gets really, really large, both of these guys are going to be 0. So this limit is going to be 0. So by divergence test, this is going to be inconclusive. If the limit is 0, then I can conclude if this guy converge or diverge. So as I said earlier, let's actually try the ratio test. Now, if I use the ratio test, I'm going to compute the limit of a sub n plus 1 over a sub n when n goes to infinity. So this is going to be the limit when n goes to infinity of, let me see, a sub n plus 1, the n plus 1 term of this series is going to be n plus 1 minus 4 over n plus 1 factorial over n minus 4 over n factorial. Now then, I can work this out a little bit. It's going to be the limit when n goes to infinity of, let me see, n minus 3 over n plus 1 factorial times n factorial over n minus 4. Thing then get cancelled out a little bit. I'm going to have n plus 1 here. So I'm going to be left with, let me see, I'm going to be left with the limit of n minus 3 over, if I multiply these two things, I'm going to get n squared minus 3n and then minus 4 when n goes to infinity. Now then, I can divide n squared both numerator and denominator. So I'm going to get the limit when n goes to infinity of, let me see, n minus 3 over n squared over n squared minus 3n minus 4 over n squared. And this is going to give me the limit of 1 over n minus 3 over n squared divided by 1 minus 3 over n minus 4 over n squared. And now when n gets really, really large, this guy will just be 0. So I'm going to be left with 0 over 1, which is 0. And then, because this guy is less than 1, that means I can conclude using the ratio test that this guy is going to converge. But there is one problem here. Again, whenever we use the ratio test, all the terms have to be positive. All terms must be positive. But if we look at the terms in this series, so if we write it out a little bit, so let me see. So when n is equal to 1, I'm gonna get negative 3 over 1 factorial. When n is equal to 2, I'm gonna get negative 2 over 2 factorial, and then negative 1 over 3 factorial, and then 0 over 4 factorial, and then 1 over 5 factorial, 2 over 6 factorial, 3 over 7 factorial, 4 over 8 factorial, and so on. Now then, it seems like I can almost use the ratio test. I mean, most of these terms are going to be positive, except that some of the few first terms that we have here, only the first 3 terms are negative, and this guy is just 0. Well, there is a way that we can fix this. So let me go back to the second principle here. In a nutshell, this second principle says that we can ignore the first few terms. We can ignore the first few terms in the series. We can ignore the first few terms. The first few terms in the series. In other words, let's say if I'm trying to find if the sum of a sub n when n goes from 1 to infinity, which is this really long sum of number a1 plus a2 plus a3 plus a4 plus a5 plus a6, so let me just do this to a7 and so on. Well, this is actually just an infinite sum of number that's going to be a really long list of number being added. So then maybe I don't really have to care about the first few terms here. So let's say maybe I don't really have to care about the sum of the first 3 terms because this is just a number. So I can just look at the tail. If this guy converge, then if I add the number to a number, then this whole thing should also converge. On the other hand, if this guy diverge, maybe it blows up with this infinity or maybe it doesn't exist, then if I add a number to that thing, it will not help. This whole thing is also going to be infinity or it will also not exist. So what this second principle say is that we can ignore the first few terms in the series. Instead of starting off at 1, I can start off at whatever value I want, and this 2 series is going to have the same convergence and divergence status. So then, if I go back to my example here, even though not all the terms in this series are positive, but we can see that these guys are all positive. And that is actually good enough. This is good enough to use the ratio test now. So then I can conclude using the ratio test that this series is going to converge. So let me just say converge here. And by the way, just a quick comment, we can also decide whether this guy converge or diverge using also the comparison test. So most of the time we can actually, there's more than one way to tell if a series converge or diverge. So comparison test. I can compare n minus 4 over n factorial with n over n factorial. And we can kind of see n minus 4 over n factorial is going to be less than or equal to n over n factorial, which is just 1 over n minus 1 factorial. And we can look at these series. Now I can again use the ratio test and conclude that this guy is going to converge. This guy is going to converge. And because the series in the question is even less than or equal to the guy that converge, so that means this guy also has to converge. But once again, some of the terms here are gonna be negative, so we have to argue. So some of the terms here are gonna be negative, so we have to argue using the same principle that because we can ignore the first few terms that are negative, but most of the terms here after n equal to 5 and so on are gonna be positive. So then we can use the comparison test to conclude as well that this series is going to converge. So now let's look at the next one. We have seen this already and we have tried the root test. The root test, we're gonna compute the limit of the nth root of the terms of this series. So we would like to find the nth root of this thing. And it turns out this is going to equal to the limit when n goes to infinity of, let me see, n plus 1 over n, which is going to equal to 1. So we can't decide if this guy is going to converge or diverge using the root test. So let's try something else then. Maybe we can use the comparison test. But then we have to decide what we are going to compare with. Maybe we can compare n plus 1 over n to the n with just n over n to the n. And let's see what is going to happen here. My left hand side is definitely bigger than or equal to my right hand side. And my right hand side, this is just the sum of 1 to the n, which is just the sum of 1 when n goes from 1 to infinity. Now, this is basically just a sum of a bunch of 1, so this guy definitely diverges. And because this guy diverges, then the original series in the question will also have to diverge. So we can now conclude using the comparison test that this guy is going to diverge. Or once again, let me try another test. Let's try the divergence test as well. So let me try the divergence test. To use the divergence test, I'm gonna find the limit of a sub n, which is n plus 1 over n to the n when n goes to infinity. This is gonna be just the limit of, let me see, this is going to be the limit of 1 plus 1 over n to the n, which, by the way, is going to equal to e. And because this doesn't equal to 0, so that means I can use the divergence test to conclude that this same series is going to diverge as well. So as usual, there's more than one way to tell if a series converge or diverge. Now let's take a look at the last one. This last one, once again, is something that we have seen before, so let's try divergence test. If we use the divergence test, I'm gonna compute the limit of log of n over n squared when n goes to infinity. Now then, this guy is going to equal to 0. In fact, we have done this already in example, let's see, 3.4. So, because the limit is 0, that means the divergence test is going to be inconclusive. Let's try something else. Maybe we can try comparison test. To use the comparison test, I'm gonna have to come up with another series to compare with this one. Maybe I can try, there's not many series that we know that have the log n, so let me try to compare log n over n squared with 1 over n squared, and we know that this log n is going to be bigger than or equal to 1, so I have something like this, and this guy is a p-series with p equal to 2, so this guy is going to converge. But then that means I can't really conclude anything about the divergence or convergence status of this guy, because this is bigger than or equal to something that converges. So the series in the question, it may converge or diverge. So using this comparison, I can tell if this guy is going to converge or diverge. If I use limit comparison, that's also going to give me the same outcome. If I try limit comparison, okay, limit comparison. So I'm going to compute the limit of the ratio of the two series. So I'm going to compute the limit of log n over n squared over 1 over n squared. This is going to be just, this is n equal to infinity. Let me actually write limit here. Limit comparison test. So this is going to be the limit when n goes to infinity of log of n, which is going to be infinity. So that means limit comparison test with this series also doesn't work. Limit comparison test only works when this limit is a number, is a real number that is not 0. So for if I get infinity, then that doesn't work. So let me try something else. Well, let's try ratio test. Let's see if I try ratio test. I'm going to compute the limit of an plus 1 over an. So that is going to be log of n plus 1 over n plus 1 squared over log of n over n squared. This is going to be the limit. This is going to be equal to the limit of, let's see, log of n plus 1. Let me rewrite it this way. It's going to be log of n plus 1 over log of n times n squared over n plus 1 squared. Now we can compute the limit of these two guys using the L'Hopital's rule, and they are both going to equal to 1. So this is going to just equal to 1. Now then, when the limit of the ratio is equal to 1, then I can conclude anything using the ratio test. So once again, this is inconclusive. Well, let me try root test then. If I try the root test, I'm going to compute the limit of the nth root of the terms in this series. So it's going to be the nth root of log of n over n squared when n goes to infinity. And this looks troublesome because the nth root of log n over n squared, that doesn't look like something easy that I can compute. So this is too hard. Let me just skip that. So that means the other option that we can try is the integral test. So I would like to try now the integral test. So I would like to compute this integral, the integral of log of x. So I'm going to change from, let's see, log n over n squared to a function. So that is going to be log of x over x squared dx. And I'm going to integrate this from 1 to infinity and see whether this integral, this improper integral converge or diverge. But before we can use the integral test, there are conditions that we have to check. We have to see if our function, which is log x over x squared here, is continuous, positive, and decreasing. Well, for this function log of x over x squared, this guy is definitely continuous, and it is definitely positive because log of x is going to be positive when x is bigger than 1. Log of 1 is 0. Okay, so this guy is definitely positive, and x squared is definitely positive. So the ratio log x over x squared is definitely a positive function. But now I have to decide if this guy log x over x squared is decreasing. So how can we decide if a function is decreasing? Well, we have to look at its derivative. So my function is log x over x squared. And I need to see if this guy is going to be positive. It's going to be decreasing. So I look at its derivative. The derivative of this guy is going to be, let's see, it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom. The whole thing over bottom square. X bottom square. So that's going to be x square. So that's going to be x to the 4th. Now this is going to give me, let's see, x minus 2x times log of x. The whole thing over x to the 4th. So this is going to be 1 minus 2 log of x over x cubed. For a function to be decreasing, I'm going to need its derivative to be negative. So I like to decide if this guy is going to be less than or equal to 0 or not. Now then, when x is large enough, I can see that x cubed is going to be positive, but 1 minus 2 log of x is going to be negative. So then if I divide something negative by something positive, then I'm going to have something negative. So this should work. By the way, I have this principle that we see earlier, that we can ignore the first few terms of the series. So for the first few value of x, this guy might be positive, but that is okay because when x is large enough, this numerator is going to be negative. So I can now conclude that this function log x over x squared is going to be decreasing. So now I can use the integral test. Now then, well, this is going to be a long example. I have to integrate this guy. So this is going to be, well, it's improper integral. So I have to rewrite this as a limit of the integral of log of x over x squared when the integral goes from 1 to n and my n is going to infinity. Now then, to find this integral, let me kind of do that on the side here. To find this integral, I'm going to have to use the integration by part. So here, if I want to integrate, let's see, log of x over x squared dx. So let me see, if I let my u to be log of x, and I let my dv to be 1 over x squared dx. Well, if my u is log of x, then my du is going to be just 1 over x dx. And if my dv is 1 over x squared dx, this is the same as x to the negative 2 dx, by the way. So then my v is going to be just the integral of this, which is x to the negative 1 over negative 1. Now I can rewrite this as negative 1 over x, by the way. Negative 1 over x. And this makes sense because if I take the derivative of negative 1 over x, which is negative, okay, let me write this, negative of x to the negative 1, the derivative of this guy is going to be x to the negative 2, so this is going to be my v. So now this integral is going to equal to u times v, which is log of x times negative 1 over x minus the integral of v du, which is going to be, let's see, negative 1 over x times 1 over x dx. Now let me kind of move this somewhere. Let me try this. Let me move this up here, so then I can move this to the side. Okay. So now, if we try to finish this integration, let's see, the first term is going to be just minus log of x over x. And this integral, the negative sign get cancelled out, so I'm going to be plus the integral of 1 over x squared dx. The integral of 1 over x squared, we have just done this, is going to be negative 1 over x. So this is going to be negative 1 over x plus c. Now then, I can evaluate this integral now. So this is going to equal to, let's see, the limit when n goes to infinity of this integral, which is going to be negative log of x over x minus 1 over x, and I'm going to evaluate this from 1 to n. Okay, so it's going to be the limit when n goes to infinity. If I plug in x equal to n, I'm gonna get, let me see, negative log of n over n minus 1 over n minus, I plug in x equal to 1, so it's going to be log of 1 over 1 minus 1 over 1. So now I like to compute the limit of this guy when n goes to infinity. Let me try to simplify this a little bit. The limit when n goes to infinity. The terms in my bracket here is going to be, let's see, minus log of n over n minus 1 over n, and then there should be a negative sign here, by the way, so this should be negative log 1 over 1. Now log of 1 is 0, so this thing is going to be just plus 0, and then this two negative sign will cancel out to a plus 1. If I compute this limit, I'm gonna have that the limit of 1 over n, this is going to be 0, and the limit of log of n over n, I can use the L'Hopital's rule here and conclude that this is also going to be 0, by the way. So let me kind of do this over the side here. If I want to compute the limit of, let me see, log of n over n when n goes to infinity, I can use the L'Hopital's rule because this is of the form infinity over infinity. Then the derivative of the top is going to be just 1 over n. the derivative of the bottom is going to be 1. So this is just the limit of 1 over n, where n goes to infinity, which is going to be just 0. So then I can conclude that this whole limit is going to just equal to 1. So after a long work, we can conclude that this integral is going to equal to 1. So that means this is not infinity, it definitely exists. So this integral converge. So then I can go back and conclude that the original series is also going to converge. And that's the last series for this example and for this lecture as well.